Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. This is it. We are finally going to prove some general completeness results. In this video, we're going to do two systems. System K, because that's the dead simple easy one, which doesn't actually involve any proving. It just involves like pointing things out. And System T, which is quite straightforward, but it gives us an idea of what it is that we need to do to go about proving the completeness of more complex systems. So let me bring up the whiteboard because we are definitely going to need it today. And again, I'm just going to summarize a bit of some of the things that we talked about in the previous video so that we've got everything all in one place. So the idea for completeness is that we want to show that if some formula phi is valid on a class of frames, so this means that in every frame, at every world, no matter what the valuation is, that formula is true, then it is possible to prove it in some relevantly chosen, appropriately coordinated system S. This is what the statement of completeness is. So the thing to think about here, the important thing to keep in mind is that we're going to be looking at the contrapositive version of this, which is to say that if in some system S we have a formula phi which is not a theorem, then it's not going to be valid on that class of frames. That means within that class, we can find a frame, a model on the frame, and a world within that model where that formula phi is false. This is where the canonical model comes in, because recall that in the canonical model, every non-theorem is falsified in at least one world. So in the canonical model for a system S, every phi which is not a theorem of S is falsified in at least one world. Could be more than one, doesn't really matter. The important part, though, is then if we can show that, so if we can show that the frame that underlies that canonical model is a frame in that class C, then we have our desired result. Because what we want to show is that if something's not a theorem, then it's not valid in the class of frames. We know that if it's not a theorem, it's not valid in the canonical model. And if the canonical model is based on a frame that is in that class of frames, we then have what we need. So that is a slightly more kind of technical way of talking us through the conceptual stuff I was doing in the previous video. That means we have a very straightforward theorem for the completeness of K. So the theorem is the frame, I'm going to call it Fk, of the canonical model Mk, so that's the canonical model for system K, is a member of the class of K frames. So that is what we want to show. So it's a member of the class of K frames, that is, frames which validate all the axioms of K and all of the theorems and everything. And now, hopefully, you can see why the proof of this is so easy. This is because the class of K frames is the class of all frames. So it's a frame, it's a member of the class of all frames. So the class of K frames is just the class of all frames. Done. Okay. See, that's what I mean about this one being so straightforward, it doesn't actually help us understand how the canonical models method works. So let's do something a little bit more interesting. And that is going to be looking at system T. So what we are going to prove is that the frame Ft of the canonical model MT, so this is the canonical model for system T, which is K plus the axiom, box phi implies phi, is a frame for T. Now, the class of frames that we are interested in, the class of frames for this logic, is the class of reflexive frames. So what we need to show is we need to show that, so we need to show that Ft, the underlying frame of the canonical model, is reflexive. And then it will be within the relevant class of frames, and we will get the result that we want. So this is because T is characterized by the class of reflexive frames. So what we need to show is that, so to show that the frame of the canonical model is reflexive, what we need to show is that for every maximal T-consistent set gamma, it is the case that gamma sees itself. So if we look at what the definition of R, the accessibility relation, in the canonical model is, this means that, so by the definition of R, what we need to show is that the box minus of gamma is a subset of gamma for an arbitrary gamma, because that will get us, what you can see is that this is just another way of saying, so that is, if box phi is in gamma, then phi is also in gamma. So this is a hypothetical. What we're going to do is we're going to assume the antecedent and then show that the consequent follows, and we're just going to do it for an arbitrary gamma, so it will hold for any gamma whatsoever. So what we will do is we will assume that box phi is in fact a member of some arbitrary maximal T-consistent set gamma. Now, by one of the results that we showed earlier, which says that any axiom for a system is a member of every consistent set for that system. So I will just say by earlier proof, we know that every axiom of T is in every maximal T consistent set. So that means that we have necessary phi implies phi is a member of gamma because this is system T. And then we also had another earlier result, which showed that if you've got a conditional and its antecedent, you also have to have the consequent. Well, look at this. What have we got here? We have box phi is in gamma. We have that box phi implies phi is in gamma. So it follows from these two and the earlier general results that we had that phi is in gamma. And what's that? That's exactly what we needed. So this is quite a simple result, but it shows you the sort of things that we need to do. What you have to do is using the information, the fact that the axiom is going to be in every world in the canonical model, we'll be able to use that to generate the result that the frame for the model has to satisfy the right condition. And this goes back to all of the correspondence results that we did, showing things like validity, of box T implies, or box phi implies phi directly corresponds with reflexivity. If you have a frame which has an irreflexive point, then you will always be able to falsify this particular axiom. So if it is valid, then it has to have this. If it's valid on the frame, then it has to have that particular property. So this gets us part of the way to proving the canonicity, the completeness of S4, because S4 is T plus transitivity. So we will be able to just inherit this result when we look at S4. We'll look at S4 because it then shows us what we need to do with transitivity. We'll look at system B, which gives us symmetry, and then B plus S4 will give us the completeness for S5. But then we'll look at a couple of other examples which are somewhat more complex because they will require us to show the existence of particular maximal consistent sets in order to demonstrate that we've got the right relation, the right properties on the accessibility relation. So not all of them are going to be as easy as System T. A lot of them will be, but I'll hopefully be able to give you enough of a variety of examples so that if you were presented with a novel system where I say, here's an axiom, here's the condition it corresponds to, show that the canonical model of the system containing this axiom has this frame condition, you would be able to go off and do it yourself. So that's what we have to look forward to. We're going to give a couple of examples and then we'll be almost all the way there. Now, I should say, this is only one way of proving completeness, but it's a really cool way. And that's why we're going to spend so much time looking at varieties of different types of examples because it generalizes really nicely, is super useful, and once you figure out the knack for it, it's pretty fun. Until then, take care. Cheers.